you're made of atoms. Right now. Billions of them. Tiny, invisible, ridiculous. And for most of human history, we just accepted that. Cool atoms. Whatever. Can't touch them. Can't see them. Can't do anything with them. Just vibes. Then some scientists said, what if we could? N. Not study atoms. Not measure atoms from a safe distance like they're radioactive celebrities. Actually grab them. Move them. Stack them like Lego bricks, one by one, until you've built something that does something. Something real. Something that could change literally everything about how medicine, computers, and materials work. That's nanotechnology. And it's already here. Okay, but first, how small are we actually talking? Because nano gets thrown around a lot. Nano this, nano that your phone has a nano chip. Sure, cool. But do you actually feel the size in your gut? N. Because you need to feel this. Wah. A nanometer is 1/1000th of a meter. 1/1000th. Your hair is about 80,000 nanometers wide. A single red blood cell is 7,000 nanometers across. A DNA strand is 2 nanometers wide. And a hydrogen atom, the smallest atom that exists, is about 0.1 nanometers. So when scientists talk about building stuff at the nanoscale, they mean building stuff that is literally the size of a few molecules. Sometimes, a few atoms. We are talking about the absolute basement of physical reality here. This is the domain where the normal rules start to break. And I mean that literally. The physics you learned in school, the physics of cars and balls and ramps and friction, that's called classical physics. It works great at human scale. It does not work at nanoscale. At nanoscale, quantum mechanics takes over. And quantum mechanics is basically the universe running on completely different software. Here's a perfect example. You know what gold looks like, right? N. Yellow. Shiny. That's the whole thing. Gold has been gold-colored for all of recorded human history. Kings wore it. Pharaohs were buried in it. It's literally called gold. The color is in the name. Take a chunk of gold. Grind it down smaller. Still yellow. Grind it smaller. Still yellow. Keep going. Keep going. Get down to gold nanoparticles. Particles just a few nanometers across, and the gold turns red. Red. Burgundy, actually. Sometimes orange, sometimes purple, depending on the exact size. The same element. The same atoms. Just arranged in a smaller cluster. Why? N. Because at that scale, the electrons in gold can no longer move freely through a big chunk of metal. They're confined to a tiny space. Quantum confinement. And when light hits those confined electrons, they absorb and reflect different wavelengths than they would in bulk gold. The color literally changes. This isn't a trick. It isn't a coating. It's the same gold. Physics just works differently when you get that small. And gold isn't alone. Silver nanoparticles can look yellow or orange. Copper goes green. Titanium dioxide, which is white as a powder you'd use in sunscreen, becomes completely transparent at nanoscale, which is why your sunscreen doesn't look like chalk paste anymore. The material is the same. The size changes everything. So now you're starting to feel it, right? The nanoscale isn't just very small. It's a different world with different rules. And once scientists figured that out, they stopped just studying it and started asking a genuinely dangerous question. What if we could build things there? Not discover things. Not measure things. Build things. Design them. Engineer them atom by atom with intention, the way an architect designs a building, except the building is smaller than a virus and it runs on quantum physics. That question is what kicked off the entire field of nanotechnology. And the answer turned out to be, yes, we can build things there. Some of those things are incredible. Some of them are terrifying. And at least one of them became a meme. But first, we need to talk about carbon. Because carbon is the atom that started showing off. Carbon is ridiculous. It's the 6th element on the periodic table. It's in your body, in the air, in every living thing on Earth. Totally normal element. Completely unremarkable at a dinner party. But carbon has a secret. Its personality changes completely depending on how you arrange its atoms. You know graphite, right? N! The stuff in pencils? That's carbon. Soft, gray, leaves marks on paper. Kinda boring. But arrange those same carbon atoms into a different pattern, a 3-dimensional tetrahedral lattice, and you get diamond. Hardest natural material on Earth. Transparent. Worth a ridiculous amount of money. Same element. Completely different arrangement. Completely different material. Okay. Now, hold on. Because we're not done. In 1985, scientists discovered a 3rd form of carbon. They were blasting graphite with a laser totally normal Tuesday, and found that carbon atoms were spontaneously assembling into perfect hollow spheres. 60 carbon atoms arranged into a soccer ball shape. They named it Buckminster Fullerene, after the architect who popularized geodesic domes. Everyone calls it a buckyball. It is, genuinely, a soccer ball made of 60 atoms. It is one of the most symmetrical molecules in existence. It bounces. It's hollow, so you can trap other atoms inside it and use it as a drug delivery system. It's a superconductor under certain conditions. It's one of the most scientifically useful shapes ever discovered, and scientists found it by accident, while making soot. Then, in 1991, someone figured out how to roll a sheet of carbon atoms into a tube. Carbon nanotubes. And this is where things get actually insane. Here's the question. What is the strongest material a human being has ever made? Steel? Titanium? Kevlar? Wa. Carbon nanotubes are roughly 100 times stronger than steel at 1/6 the weight. They conduct electricity better than copper. They conduct heat better than diamond. They can be made into transistors that are faster than silicon. A cable made from carbon nanotubes, if you could make one long enough, could theoretically extend from Earth to geostationary orbit and not snap under its own weight. This is the concept behind the space elevator, which sounds like a sci-fi movie, but is an actual engineering proposal that scientists take seriously. 100 times stronger than steel, made of carbon, the same element as the graphite in your pencil. This is the awe moment. Sit with it for a second. The difference between pencil lead and a cable strong enough to hold a space elevator is just the arrangement of atoms. That's it. No different ingredients. No exotic materials from another planet. Just carbon atoms organized differently. The information encoded in the structure is everything. The atoms themselves are almost beside the point. This is the deepest idea in all of nanotechnology. Properties don't come from what things are made of. They come from how they're arranged. And then came graphene. One single layer of carbon atoms. One atom thick. Arranged in a flat hexagonal lattice. The same pattern you see on the background of this video right now. It is the thinnest material ever created. It is also, pound for pound, the strongest material ever tested. It conducts electricity at room temperature faster than silicon. It's nearly transparent. It's flexible. It's an almost perfect barrier. Even individual helium atoms can't pass through it. It exists at literally the minimum possible thickness for a physical object to have. It was first isolated in 2004. With Scotch tape, by Andrei Geim and Konstantin Novoselov, who were goofing around on a Friday afternoon experiment, peeling layers off graphite with tape until they got down to 1 atom thick. They won the Nobel Prize in Physics in 2010 for that tape. Friday afternoon. Scotch tape. Nobel Prize. Okay, so now we have materials that bend the rules. We have quantum effects that change colors. We have carbon doing things that carbon has absolutely no business doing. But materials are just the start. Because here's where nanotechnology stops being a materials science story and becomes something way more interesting. What if you could build a machine? Not just a material. A machine. With moving parts. At the nanoscale, an actual molecular motor. A rotor that spins. A hinge that opens and closes. A device that converts chemical energy into mechanical motion, the same basic thing your muscles do, but built from individual molecules, running at the nanoscale, doing targeted, programmable work. These exist. They are not theoretical. Scientists have built molecular cars with 4 wheels and an axle, molecular elevators that go up and down, molecular switches that flip between 2 states. In 2016, the Nobel Prize in Chemistry went to the scientists who designed them. We have nanomachines. We literally have nanomachines. Which means, you know what's coming. We have to talk about that one meme. Nanomachines, son. If you know, you know. If you don't, it's from the video game Metal Gear Solid 4, where a villain named Senator Armstrong reveals that his insane physical strength comes from nanomachines injected into his body. The meme has been going strong for over a decade because it's so absurd. A roided up senator punching through metal while screaming about nanomachines. Except here's the thing. It's not that absurd anymore. The real nanomachine story isn't about a senator. It's about cancer. And it might be the most important medical development of the 21st century. Here's the problem with chemotherapy. When a doctor gives you chemo, the drugs travel through your whole body. They can't tell the difference between a cancer cell and a healthy cell. They just kill fast-dividing cells. Cancer cells divide fast, so they die. But so do your hair follicles, your gut lining, your immune cells. Chemo works, but it's essentially carpet bombing your entire body and hoping the cancer loses more than you do. Now here's the question. What if you could deliver the drug only to the cancer cell? Not nearby. Not in the area. Directly to the cancer cell. One cell. Targeted. Precise. With a molecular lock that only opens when it recognizes the specific protein signature on the surface of a tumor. This is what nanoparticle drug delivery does. Researchers have built lipid nanoparticles, tiny fat bubbles the size of a few hundred nanometers that carry a drug payload inside, coated with molecules on the outside that bind specifically to cancer cell receptors. The particle circulates through your blood. Healthy cells ignore it. A cancer cell's surface proteins grab onto the coating. The particle gets absorbed. The drug releases inside the cancer cell. The cancer cell dies. The healthy cell next to it is completely fine. This isn't future talk. mRNA vaccines, yes, the COVID vaccines, used lipid nanoparticles to deliver the mRNA instructions into your cells. You already had nanomachines in your arm. You didn't even know. And researchers are going further. DNA origami, which is exactly what it sounds like, folding DNA strands into programmed 3D shapes, has been used to build nanoscale cages that carry drug molecules, stay closed in healthy tissue, and pop open specifically inside cancer cells. A cage made of DNA. That opens on command. Inside a cell. This is real. This has been demonstrated in lab settings. Clinical trials are ongoing. The nanomachine future isn't coming. It's already in a test tube, and it's walking toward us. But okay, we need to talk about the scenario that makes people nervous. The one that gets brought up every time someone mentions nanotechnology at a party and accidentally clears the room. Gray goo. In 1986, an engineer and futurist named Eric Drexler wrote a book called Engines of Creation. In it, he proposed the idea of self-replicating nanomachines, tiny robots that could build copies of themselves using raw materials from the environment. The idea was that these machines could manufacture anything, atom, by simply copying themselves and building. Unlimited production. Total molecular control. But then he asked, what happens if they can't stop? A self-replicating nanomachine that keeps copying itself, consuming all available matter to do so, would spread exponentially. Carbon from wood. Iron from soil. Oxygen from air. Everything gets consumed and converted into more nanomachines. More nanomachines means more replication. More replication means faster consumption. You end up with the entire surface of the Earth converted into a gray, featureless slurry of nanomachines that have nothing left to eat. Gray goo. Every molecule on Earth. Gone. In a matter of days. Here's the thing, though. Most nanotechnologists today think gray goo is not actually the threat. Real nanomachines are incredibly fragile. They break down constantly. They require very specific chemical conditions to operate. Building a self-replicating system that also survives real-world conditions, temperature changes, humidity, radiation, chemical interference, is so hard that the engineering obstacles alone make runaway replication extremely unlikely. The real risks of nanotechnology are more boring and more real. Nanoparticles that enter the lungs and cause inflammation. Environmental accumulation of synthetic nanostructures. Nano-enabled surveillance. The same precision that lets a nanoparticle find a cancer cell could theoretically let it find a specific person's cells. The power to act at the atomic scale cuts both ways. Every tool in history has. So zoom out. We started with a question. What happens when science starts playing with atoms like Lego bricks? And we got materials that are simultaneously the strongest and thinnest things ever made. We got gold that isn't gold-colored. We got carbon that holds up a space elevator. We got drug delivery systems that speak the language of individual cells. We got molecular machines with moving parts small enough to fit inside a virus. And we're at the very beginning of this. The transistors in your phone are already down to just a few atoms wide. We are approaching the physical limit of miniaturization. What happens after that? What's the next paradigm when silicon runs out of room? Nobody knows. That question is genuinely open. The answer might be quantum computing, or biological computing, or something that nobody has thought of yet. But here's the thing that should keep you up at night, in a good way. Every material property you take for granted, the color of gold, the hardness of diamond, the conductivity of copper, none of it is fixed. It's just the default setting. At the nanoscale, those settings can be changed. New properties can be designed. New materials can be engineered that have never existed in nature because nature never needed them. We are at the moment in history where we stopped finding materials and started designing them. The Lego bricks were always there. We just learned how to read the instructions.